Well, good to see everybody after lunch. There's actually a lot more people in here than I expected, given the 8-minute timeline that Riley told us to get back over here. So good work. Pretty excited about being able to present today, be able to talk more from a high level about fastening systems, some of the nonlinear track modeling that we've been working on. Definitely want to thank Mateus Trizotto, former graduate student that was working with me, who's now working with Voestalpine Nordtrack. Definitely this work wouldn't be possible without him, so I definitely want to say thanks to him. So if you have really, really hard technical questions, go ask him. If not, I'll do my best to answer them. Just to give a little map of where we're going, about half my presentation is going to focus looking on the why we're doing work, and then the back half will be what we actually did using this nonlinear modeling to be able to understand what are the demands that our fastening systems, or actually if you take a step back, that the track is seeing, and what is the impact of changing out a given component. And then I'll finish it up with just the final remarks and conclusions. And as I mentioned, I kind of want to take a step back. This is a fastening system presentation. Riley hit on this a little bit in the opening, being able to talk about mechanistic empirical design, because traditionally track has been undertaken in one of two methods. The first would be a mechanistic approach, actually going out, quantifying what are the displacements, what are the strains or stresses that components are going to feel, make sure that we're using the right materials so that we don't yield them, we don't break them. The other approach is empirical. And I think we've all experienced this as well of, well, we have a problem, let's throw something out there. Oh, that didn't work, let's make it bigger, let's use a different material, it still breaks, let's try it again. I think we've seen both of these approaches, but actually a vision that we really want to put forward is being able to take the best of both of these. Because all the models and analytical tools that we come up with, they're just that. They're these models and tools, and we have to be able to link these results, these stresses, these strains, to the empirical evidence. How are they performing in track? How many tons are they being able to withstand? And so Riley, again, hit on this a little bit. This isn't brand new. It's new to track design and component design, but the pavement design, MEPDG, has been out for a few decades now and being very successful. And so what does this look like? It requires data, which is great because more and more we're gathering more and more data. And it's just, how can we use this? Being able to get the loads, knowing the environment, knowing the types of ties or track components that we're putting out there, knowing those responses. So we need analytical tools, or we need to go out and instrument these components to be able to see how are they performing, what are these stresses or displacements they're being subjected to, given the certain loads. And then how can we forecast this? This is where we're going to start needing either better analytical models or starting to take the big data that we're getting to start getting this degradation prediction given a certain load, given a certain type of displacement or stress within the components. You then need to set your failure criteria, and this can be set from a railroad's perspective. Each railroad can have their own thresholds. And in general, you would probably say, I'd rather fail up high in my fastening system than down low in my subgrade, where it's going to be a pain to actually go out and fix. So you can set your failure criteria appropriately. Go back and say, did we design, do we come up with the right initial conditions? If no, try again. If not, sure. But then you need to ask, is this optimized? There's a lot of components that are out in the industry or out in the field that have very large factors of safety. And then can we actually optimize the design to give us the best life cycle cost that is still maintainable? And so we can end up with a final optimized design. And an example of a suboptimal design and over-designed system, whenever we've done some of the concrete tie work and we look at the factor of safety between the initial cracks that we see to the final ultimate strength of those ties, you can get a factor of safety between 3 and 5, and on a transit it might be a factor of safety of 10. And do not satisfy design requirements. I think we can all come up with examples of components that are just failing prematurely, and maybe they didn't before, but now that we're getting longer life out of our rail, now our fastening systems are wearing out, or our ties are wearing out because we're not staying on top of some of the maintenance. So we need to go out and quantify the demands on these components. And there's a lot of work that's actually already gone on in the industry. We have experts that have focused in the ballast and substructure, cross-tie fastening system. And these are just examples of people that have done great work. But there's very little information that's actually doing the empirical work, at least that's widely available and shared with other people. And sometimes the information that we learn about the stresses, strains, whether it's on the substructure or on a fastening system, on a tie, we're not relating it to that information that the railroads have. And so there's this disconnect. We have silos of data that aren't speaking to one another, and we need to actually be able to combine people and communicate a little bit better. And so that's the vision for where this can go. Putting that in context of trying to be able to improve design, we also just ask, we're in a fastening system session. I imagine many of you are well versed in what fastening systems do and what they are how they're designed. But for anybody who's not, they have to transmit vertical, lateral, longitudinal loads, maintain proper gauge, and be able to provide appropriate levels of creep resistance. And as your track is increasing in class, or as your loads are increasing, or your tolerance, or you're asking your fastenings to do more, you need to change your track components. And I want to break this up and think about what are fastening systems supposed to do when we're applying vertical, lateral, or longitudinal loads. And we'll start and we'll go from maybe an industry track or a low class track where we can get away with plates, spikes, timber ties, every other tie, every third tie anchored. But as we ask this track to do more, as we go to a class 3, or if we go into curves, for example, we're going to need to increase the number of spikes for our lateral gauge restraint to hold those plates in place. We might have to add an elastic fastener to be able to improve our rail rollover restraint. This allows us to get rid of anchor, but now you can have an elastic fastening system for the longitudinal resistance. And if you need additional strength within your track, you can go to concrete ties, change out some of your fastening system components or your slab. So there's different ways to think about how we're already trying to optimize the track condition, and we're just trying to get additional information to be able to make better decisions of when we should use different types of track. And one of the reasons why I want to break it up of what are these fastening systems supposed to do in the 3 different directions is because when we think about failures of fastening system components, and again, this is a non-exhaustive list, but this shows quite a few ways in which fastening systems can fail. I'd argue that most fastening system failure modes are driven from multiple directions. It's not just one load that's causing failure. Let's take rail seat deterioration, which Riley again alluded to whenever he kicked off the conversation this morning. I would argue that this is a fastening system problem, and it's driven by all 3 directions. The lateral and longitudinal loads can either rip your pads out of the fastening system if they're not in there tight, or they're at least going to move it around and cause abrasion. If you don't have high vertical loads, you likely won't get high pressures, and therefore that movement is going to be non-destructive. But once you get all 3 loads working together, now you're going to have a lot worse conditions. And I would propose that many of these fastening system failure modes are requiring multiple load directions. And so I think that's important for us to know, important for fastening system companies to be able to think about, are we taking into account all 3 directions? Because even the longitudinal loads are involved with most of these failure modes, it's one of the load directions that we know the least about. It's hard to actually say what is the demand that's going into our fastening system or going into a specific component. We have ideas, but it hasn't been quantified nearly as much as the vertical and lateral. One other motivation behind us working on a nonlinear track model is being able to advance rail safety. When you actually look at the number of derailments that have occurred between this 20-year span that we pulled the data, it was more than 12 per year just due to defective fastening systems. And so if we can improve the design and come up with more optimized designs, we're already going to be able to improve rail safety. And so given that there's been a significant amount of work looking at vertical load paths, and even better work now that Ricardo has been able to present his model that I don't even remember all the names of it, which is really good. There's been some information provided on lateral and longitudinal forces. There is this opportunity to advance it. Instead of having a limited number of data that we've quantified or tools that can give us lateral and longitudinal loads, we need to expand this. And then we need to be able to relate them, as I referred to earlier, relate what we're seeing, the demands and the stresses, to actual performance out in the field. And so with that, we have been able to develop a 3D parametric model that we are having 700 feet long of track. The track components are discretized so that we can be able to see actually how is each component, each rail seat, each tie, how the ballast that's supporting it, how are these all interacting with one another. And we give independent lateral and longitudinal slip, because slip is really important. We know that rail is moving through fastening systems or tie is moving through ballast. And if we don't account for that slip in the system, then it's an unrealistic case. And so we also need to understand that this slip will change depending on if there's the presence of a train. And so as vertical load is present, the load that causes slip will actually increase. And so we can take that into account with this 3D parametric model. And then because 700 feet, it's not infinite track, we tried to make it seem infinite by putting on springs at the end of our section. And so we needed to validate this. We validated it against another validated model that was done by Mateus as well, this Trizotto et al. Analytical elastic model. Basically, this non-linear approach is an advancement upon his initial work for his master's. And it was validated using field data out on Norfolk Southern. And so we've got 2 locomotives applying vertical and longitudinal loads, respectively. And we have such a low longitudinal load just to make sure that no slip occurs. And whenever we're going to be looking at longitudinal fastener load, as well as the distance along the track, and we'll have the 2 locomotives sitting right at the middle. And whenever we look at the load and displacement, I have the Trizotto et al. Model with circles, and our nonlinear parametric model, ILI3D, with solid lines, and the overlap is wonderful. So we're happy with linear validation. But what happens when there's slip? We need to make sure that the slip is accounted for well and is accurate. Again, when comparing loads over distance. And so we went and found some work done by Samavidam et al. They were able to validate their model using field data, but instead of when longitudinal loads are applied by locomotives, they did rail brakes. And so our loading is actually applied by a temperature differential. So between the rail neutral temperature as set and the rail brake temperature, we can now model that and be able to see a load applied, the rail is cut, and the force is basically 0 here, increasing up to what it should be at the rail neutral temperature. And again, the overlap between the Samavidam et al. And our model was spot on. And so we're very confident that our model is able to accurately give us the loads that are going into the rail, go into the fastening systems themselves, and give us accurate displacements as well over distance. And so the first use case for this is to be able to say, how does this model compare to the Trizotto et al. That did not account for slip? And so we're going to go back to our 2 locomotive loading case, 39 kips per wheel vertical, but now we're increasing to 10 kips per wheel in the longitudinal direction to induce slip. We got our 2 locomotives. We now see the ILI3D model does not have this nice clean shape that the Trizotto et al. Model did. We're actually seeing dips in forces in between locomotives, in front of locomotives, as well as a greater peak in between those. And if we look at where these dips are occurring, it's actually where the rail is uplifting. And so slip can occur easier in between trains or before trains due to the wave action of that rail. Slip of the rail between the fastening can occur easier at those locations. And the total increased loading in this instance was 7% higher when not accounting for slip And so we're getting a more accurate model. We're being able to take into account these load reversals going between about 1,000 pounds down to 600, and that's going to add to additional load cycles that these systems are seeing. And so one of the questions that we might ask of this model is what happens when we actually go out and change different components? What happens when we change the stiffness of the components or change the strength? We can change the toe load of fastening systems. We can change the type of fastening system, which will have an impact on the stiffness or the slip capacity of that system. And so if we take our control, basically basic inputs that we can find from literature, the same loading conditions that we had before, we see that our rail seat loading is 1,000 pounds. And as we change our stiffness, whether it's high stiffness fasteners or ballast or both, we see an increase in the load that's going into our rail seat. Whereas whenever we're changing, when slip occurs within our system, so a frozen track would be high strength ballast with a low toe load, allowing lower slip values. Ultimately, what we do to change slip doesn't change that force that's going into any single fastening system as greatly as the change in stiffness. So we can see that component stiffness has a greater impact than the strength within the reasonable levels that we were looking at within this study. And even with high stiffness ballast and fasteners, we can increase the fastener loads by 50%. And what's the relationship? We can look at this a little bit more, given we know there is a relationship between stiffness and longitudinal fastener load. If we take our control value and then add in these high stiffness ballast fasteners and ballast and fasteners, we can now come up with a relationship between track stiffness and rail seat load, which helps us understand what are the demands that these fasteners need to be subjected to or designed to. And so now I'll take this to spikes, which we'll get to learn a lot more about from our next two speakers, so I won't belabor this point. But there's been a lot of broken spikes that have been occurring. They've led to multiple derailments, and we've been investigating it for the past 3 or 4 years, thanks to funding from Cam Stewart of the FRA. And what I want to look at with our model is what's the impact of fastening system stiffness due to this reduced distribution of loads. You have a stiffer system, and so how will it change the loads just by changing one system out? And so this is a case study looking at longitudinal spikes, spike breakage, and we've got 2 locomotives, same load conditions as before. We're going to hold together the ballast and other conditions, but all we're going to do is change from our anchored fastening system stiffness to our elastic fastening system stiffness, which we quantified in the laboratory. And we see that this is a 4-time greater or 4-time increase in stiffness just from the elastic fastening systems, holding all other components the same. We can see that there's a 24% increase in our rail seat load. And so when we're thinking about spike, why are our spikes failing? This is just one of those aspects that is increasing the load demand placed on our components that needs to be accounted for. And again, there's a benefit to going to the elastic fasteners to account for rail rollover, to account for getting rid of the anchors, and you're simplifying your system. But every component that we change within our system has an impact somewhere else, and we need to have these tools to be able to understand what that impact is. So this is just one tool that we have to be able to quantify what happens when you change out systems. And so as I wrap up, fastening systems are primarily failing due to a combination of loads. It's not just vertical or lateral. It's a combination of vertical, lateral, and longitudinal. We could be striving to communicate better between mechanistic data that we can quantify as well as the empirical data that how are these systems behaving. And changing from an anchored system to an elastic fastener can increase the longitudinal rail seat load by 24%. And so just being able to understand what we think might be small changes can make actually a really big change in the end. So with that, I appreciate your time and look forward to answering questions if I have any time for it.
Just covered 10 years of research at the University of Illinois.